let's move on to the first question first. So what about the fit? The TensorFlow is basically the 3 lines of code. So first line, the import something, yeah, import TensorFlow. It's obvious. We know how to do that. But the last 3 line is important because, so let's say this is my model, and then you can say it's TF keras sequential or TF keras what is that? It was model. So these two are so actually the model is much broader one. So anything you can make with the sequence model, you can make it in the TF keras model. And in this model setting, what you are going to do is just to define the layers. So it goes here, and it might goes here. This is the meaning of the model. So you just set up how many layers you are going to use and how many nodes in one layers you are going to use and what kind of activation functions you are going to use. So that's the step of the model. And then you can do the compile. And then you can actually try to find the actual numbers, the actual weights and actual biases. So that's the step of fit. So in compile, you should give at least 2 informations. The first one is, what is your loss function? And then the second one is, what is your optimizer? These two are the essential information you need to provide to the model. But you don't have to worry about the optimizer because the Adam is enough. So you don't have to try the other optimizers. So you just set the optimizer as Adam and that will be fine. But for the loss, for the regression problem, the best, not the best one, only the usual choice is either MSE, mean squared error, or mean absolute error. These two are the most obvious laws. But for the classification problems, I'm going to let you know one more loss function today. So this is the topic we are going to talk about today. So once you have your structure of your model, and once you provide your model the loss function and optimizer, then you need to actually provide the data to your model so that it will actually calculate the weights and bias here. So that is the 5th step. So you should provide what your X is and what your Y is, and then how many times you are going to run. So it's epochs. So that's the meaning of the fit. So without fit, it's something like this. Okay, I'm going to make a model. It's AX plus B, but I don't know what A and B is. So in order to use your model to predict something, you need to know, A is 1.1 and B is 2.3. Actually finding these two, not these two, but there are so many parameters, so we have to estimate. And the finding these numbers, the weights and biases, is what my model.fit is doing. So that's the fit. So what does it mean if difference between validation loss and the pure loss is big? That means your model is overfitted. So what do I mean by overfit is the following. So I'm going to explain it with a simple regression model. So suppose you have a data like this one. And you may think, it looks like this, but maybe it's not, because with some more data set, you might say that actually there's one more data, some more data sets here. But we do not know the actual shape. So your model is always, so let me say, this is your train, and this is your validation. And since you are using your train data set to minimize the loss, actually the training step will eventually try to estimate something like this, to try to find the exact shape of your trained data set. But if you apply this trained model in the actual validation set, then you will get a lot of loss. So that's the meaning of the overfitting. So how can I prevent overfitting? Well, just to reduce the number of epochs. But we do not know how much do I need, how much epochs I need for accurate predictions. So that's why we make the plot of this one. So this is the epoch, and this is loss. So your training loss is always trying to go down, but actual your validation loss, at first it goes down together with the training loss, but at some point in time, it will not go down anymore. But still the actual the loss, not the actual loss, the pure loss is going to down. So this is the point where you have to stop, because in the real test data set, probably your score is very similar to this value. So you don't have to go all the down here, because even if you go down here, your test score will be at this level. So that's the meaning of the validation loss, and the pure loss is so big. So that means it's not a good sign. Okay, for this problem, we are going to go into the okay, let me show you. So let's go to the competition 2. And I'm going to make a new notebook. So this is the competition 2. So when I run the first cell, I can see 3 different files. So let me read one of them. So it's df pd read underscore csv, and let me read the train.csv and see what's inside. it has ID column, column 1, 2, up to column 7. Okay, how about the test CSV? So now the DF contains the test.csv. So when I look at this, it has column 1, 2, 4, 6, and 7. So the column 3 is missing and column 5 is missing. And our target is to predict column 5. And let's see the submission file. And it has ID and column 5. So basically, you have to submit this one. And your score will be, your rank will be at the bottom if you submit this one. But what you have to do is to find a new value for the column 5. That's it. And then once you have this one, yeah, you can save. So once it is saved, yeah, I can view my notebook. Oh, actually, I did not, yeah, save it to here. So, okay, I'm going to edit. So the first one, second one, and note that this is the submission.csv. Then I need to save it to this notebook. So df dot to CSV, and then I can make any name that I want. So it's just a file dot CSV, and index is false. And then save the version. Okay, view. And then it has an output section, and in the output section, I think I have, yeah, file.csv. Yeah. It's a little bit slow. And then press the submit button, then the file.csv will be submitted. So if this is not you want, then ask me again. So you said, yeah, you know the submission process, but you could not make a submission model. But I don't understand why. If you can make the submission for the first competition, then you should be able to make the submission for the second competition too, because this is just the same procedure for the first competition and the second competition. Yeah, I just want you to enter your team names, because I need to know who you are. So yes, So for example, in the first competition, leaderboard, and there are lots of students, but I don't know who he or she is. So I need your name, your the Korean your the name on uh, the roster, and then I need to know your team name so that I can match you and your team name. So that's what I want. Okay. ReLU is not a loss function. ReLU is an activation function. Why ReLU is better? I don't want to say that ReLU is better. I just wanted to say that lots of people these days use ReLU. So that's the one way to say something. So ReLU is just a max of your function and 0. This is the ReLU. And the another thing is softmax, and this is 1 plus e to the minus f of x to the, and actually I'm going to talk about it today, so, but I don't remember. Oh yeah, this one. To 1. So once your f of x goes through the ReLU, no matter what your f of x is, it's something like this. So this wiggly line is f of x. But for this one, whatever your function is, when it goes through the softmax function, it looks like this. So this is 0 and this is 1. So there is no specific reason why the ReLU is better than the softmax function. But many people find that the ReLU is enough. And the one simple explanation maybe I can give is that ReLU makes your function piecewise linear, whatever your function is. So in some sense, the piecewise linear is almighty function. So you can, how many points, it doesn't matter how many points you have, you can always make a perfect fit for any number of points as long as you have enough number of parameters. But probably this is the overfitting. So, but what I wanted to point out is that the every 2 points, it is a linear. And every point, between every 2 points, it's another linear function. And the ReLU function is basically the 0 and some linear function if your f of x is linear. But once you have this, and you can probably make this one as your input to your next ReLU function, then it could be looks like this. And as you go deeper and deeper into the model, it will looks like a function like this one. So maybe that's the one way. That's the way I can explain why ReLU is nice. But the main point is, if you don't like it, you don't have to say that ReLU is the best. We can use other activation functions. Yes, ReLU activation function. Well, for this students, uh, okay. Then let's go back to the competition one and see the notebook. So this is the public notebook that I uploaded, and everything is what we did. And the point is that you make a model. So in the second competition, we use not the sequential, we use model. But first you make a model, and then you need to compile by providing two information. One is loss, the other one is optimizer. And then fit your model by providing what is your X and what is your Y. And the validation split is not it's important to whether it is overfitted or not, but it is not necessary for the submission. And the verbosity is not necessary. We just need the how many epochs and X and Y. So once you have your model, and the and you use this command, DNN. Oh, it's a different one, but it's model.predict, and it will give you a prediction, and just put this prediction to your submission file on column 5. So if you understand what you are doing on the competition one, I don't think there is any problems, because even though the names are different, it's a DNN model, but still, this is the same thing. So you fit the model and then use your model to make a prediction. So it's a model that predict, and then put your test data set, then you get a prediction, and then save it and save it to CSV and then submit. Okay, for these students, I need to see your code. So just wait, and okay, just wait. So okay, so you need to understand what you are doing. So it is not just a copy and paste. So every step there is a meaning, and for this the question, the students who ask this question, please watch the previous week's video. Then you will understand why we have to use test and test twice. Yes, that's right. So we are going to talk about the softmax function for classifications. So it's or whether it is 1 or whether it is 0. So this is actually the topic we are going to talk today. Uh, okay, this is called the learning rate. And if you don't know what learning rate is, please watch the previous and previous week's videos. We talked about a lots of times. And actually, if you really want to study the learning rate, you have to go back to the first video that I uploaded for this course. Yeah, today, I'm gonna talk about this, also. And actually, it's possible because the if you look at your loss function, it is not always decreasing. Sometimes it is increasing and decreasing and moving something like this. And and it is also possible, your validation loss is lower than your model's loss, and sometimes it is bigger and lower. And if you're, so it is also possible. So if your validation loss is lower than the modeling loss, then you need to increase, then it's a good idea to increase the number of epochs so that uh, you can find the the point where these two lines cross-sect each other. So that is probably the point that you need to stop. And actually, there is going to be lots of these points. So you need to see the whole trend, not just a specific one point. Okay, if you have some more questions, just wait because I need to move on. So for today's lecture, I'm going to go to the TensorFlow. So this is the TensorFlow. So we are going to start with the get started with TensorFlow, and then we are going back to the tutorials because the classification is so we already know what regression is and how to do that. For the classifications, we are going to take the first example in the ML Basic with Keras, and the first example is actually classification. Because for some people, the classification seems to be much easier, but for me, the regression is much easier, and then classification is the next step. So I choose in this path. Okay, so this is the basic classification and classify image of clothing. And so basically this is called the image classification, but the image is not important to us. It's just the data to me. So I'm going to run this code in Google Colab. So press this button, then you will see your Colab. And on the left-hand side, it's just an explanation. Okay, now it is connected. So now we know a lot about the TensorFlow. So the first cell, so we import TensorFlow and NumPy, Matplotlib, and then print out the TensorFlow version. So TensorFlow version. And then in this notebook, the TensorFlow will classify the image of clothing. So this is the sample image. So it's called, this data set is called the fashion MNIST sample. And so there are lots of images of clothes And our job is to predict, that image is a t-shirt or trouser or pullover dress. So there are 10 different categories. So, yeah. So yeah, I import the libraries and then also import the data set. So it's just a way we import the data set. So and then let me see what's inside. So it has train images. So there are a bunch of numbers. So for us, it's just a bunch of numbers for train data set. And actually this load into your memory, two different pieces. The one is for the train and the other one is for the test. So, and then it is also divided into two piece of information. The one is actually the X data and the other one is Y data. So X data is for our regression problems, it's column 1 to up to some columns, and train label is for us, it's column 5, or in competition 3, it's column 8. But here, train data, it looks like a matrix of matrix of matrix, but it's just numbers. And then this is not necessary, but as a human, we like to see the actual explanation instead of the numbers. So it's a t-shirt, it's trouser, but it all everything is corresponds to a specific number. So it's a 0, 1, 2, 3, and so forth. But in our problem, there are only two categories, two classes, 0 or 1. So this is somewhat a general case, but once we understand what's going on here, we can reduce it to two class problems, even though it classifies into the data set into 10 different classes. So that's the class name. And then let's see the train shape and train shape. So since this is the image data set, it's the first number is how many samples we have. So it has over 60,000 samples, and it is 28 by 28. And if you think about the image is actually a matrix. So maybe here is black, this is white, here is black, and here is another black. And when we see this one, we can see some shape. So our eyes can recognize, okay, this is trouser, this is just a sandal. But for the computer, every pixel is just a number. And since this is image, we have rows and columns. And for this specific problem, we have 28 rows and 28 columns. So this is the one sample, and it has another 28 by 28 and another 28 by 28, and all together it has 60,000 images. So that's the problem setting. And then we can also see the length of the train labels. So the length of train label is also 60,000. So that means for each image, there is a one corresponding label. And let's see what's actually inside the label. So actually, the total number of total number of elements in this array is 60,000, but it shows the first three and the last three. And first one is 9 and 0, 0. So each number is actually corresponds to its name. So first one is 9, and 9 is the last one. So last one is anchor boot. So that means the first image is the actual its class is ankle boot, and the second one is t-shirt, and the last one of the 60,000 is 5. So 0, 1, 2, 3, 4, 5. It's sandal. So we have X data set, and we have labels, which is our Y. And then it also has a test data set divided into test image, and the test image has 10,000 samples, and it is also 28 by 28 shape. And then it also has the answers, so 10,000 answers. So pre-process the data, and it's just what's inside our trained data set. So here is the trained image, and 0 means the first image. And then PLT, we know what PLT is. It's a function, plotting function. So when you plot, you will see the first image, and it looks like a boots. And actually, the first one is ankle boot. So for us, for human, we see the picture and say that, okay, this is a ankle boot. But for the computer, all of this thing is just a number. And based on that number, we are going to try to find a function which can predict 0 for this image. And so if you know a little bit about the image file, actually the color image has 3 channels: so red, green, red, RG, red, green, blue. And then every red can be arranged from 0 to 255, and that's so by specifying each numbers, it can be a color. But since we want to have all these number between 0 and 1, so divide every number by 255. So the original so that's the so you may think, this is the normalization step. So we did the normalization. So we take out the average and divide it by the standard deviations. But here, and then the result will be a number between -3 plus +3. But here, they wanted to have some value between 0 and 1, because for every pixel, so 0 plus 255 is the actual number of this pixel. And if we divide this one by 255, it will be in this range. So every number is, in some sense, is normalized so that we can get a better prediction. And actually, this normalization works really well for this model. So that's the people try to realize that, oh, normalization is a fantastic thing. But before that development, before that discovery, the people usually try to the original numbers, but the model performance was not so good. But one people find that by dividing all these things by 255, the model accuracy will be increased by 20% by just changing the numbers. So that's why the people say the normalization is a great way. But in our problem, the competition one, we tried the normalizations, but it does not work very well. So it depends on problems. So let's go. So it is just dividing. And then to see some more pictures. So this one was the first picture, anchor board, and some more pictures. And we see that these are all different pictures, but for the computer, the first one is a bunch of numbers. The second one is another bunch of numbers and another bunch of numbers. So our job is to connect the bunch of numbers to each class. So we want to build a model. So how can you build the model? So we know how to do that already. So it's a TF, Keras, sequencer. So since this is a very simple example, it uses a sequencer. And we know the last two layers already. So it's a dense layer, and the last one is a dense layer, but there is a new thing, new layer called the flatten. And what it does is simply make the matrix into a one row. So let's think about the input shape first. So our input shape was 6 or 5 because we just have 5 columns or 6 columns. But here the input shape is 28 by 28. That means our input is 28 by 28. And the flattened layer, what it does is take this shape of data set and then make it one big row. That's it. That's the meaning of the flattened layer. Then the number of row here is number of rows, number of columns. I don't care. The total number here is 28 by 28. So it's some number. So for us, it's like okay, this is column 1, this is column 2, this is column 3, but here the last one is column, I don't know, it's 700 or something. So it has lots of not the row, it has lots of columns, but the structural problem is still the same as ours. Okay, the next layer is a dense layer. It has 128 nodes. Why? Because they just find it, they just say, this is okay. And activation is ReLU, and it produces 10 outputs. So that there is a difference between this model and our model, because for the regression problems, we always produce one output because we wanted to predict just one numbers. But here, it may seem a little bit weird, but it produces 10 numbers. So why 10? Because there are 10 classes. So 10 numbers, 10 classes. And okay, so 28 by 28 is 784. Anyway, so we know what it means about the model, and then we need to compile. So in order to compile, we need at least 2 input. The one is the optimizer, the other one is a loss function. So here the optimizer is same as ours, Adam, and then loss is different because this is a classification problem. it does not calculate the mean squared error. It does not calculate the mean absolute error. It calculates something different. And what is it? I will explain. Yeah, but this is conceptually, this is the mean squared error or the mean absolute errors. So conceptually, this is the similar thing. But since this is the classification problem, they use a special loss function. And then there is one more thing, the accuracy and the matrix, and it says it's accuracy. This matrix means each unit is used to monitor the training and test steps. So it is actually not necessary. But if you want to see how my model is progressed, and you may add this matrix as accuracy in while you are for the process, for the monitoring of your training process. But for the regression problems, there is no matrix. But for the classification problem, so we can calculate the accuracy. The accuracy is total number of prediction. It's the actual correct prediction divided by total number of predictions. So maybe accuracy of 90% is, we say that, the 90% of our prediction is correct. So we can calculate that kind of matrix for classification problems. So they add the matrix here. So we have our model, and then we provide two informations, loss and the type of the type of loss and the optimizer. Of course, we add the matrix too. And then what is the last step? The last step is fit by providing actual X and Y and number of epochs. So this is it. So this is model.fit. And then train images is our input data. And train labels is our output data. And we want to see, we want to run it for 10 epochs. So let's see. Oh, it's not working. Why? So maybe I did not do something. So I saw this, and then the train image, and see the pictures, and then build the model, compile, and then fit. So now it is working. And this is great because you can see the accuracy here. So after the first epoch, the accuracy is 82% and 86%, 87. So when we see our regression problem, we see the loss is decreasing. But the absolute value of loss it does not mean anything. So we just know that the smaller value of the loss is better, but the accuracy, it says as the model trains, the loss and accuracy metrics are displayed. This model reaches an accuracy about 91%. So with this simple model, this model now can tell by showing some picture, then it can classify it is a boot, or it is a t-shirt, or it is a trouser. So which is great. And actually, that's the end of classification. Now, once you have your model, then you can use it to predict. So let me add a code here. And let me show you how we can make a prediction for a specific image. So for example, so what is the name? So I can say model predict, and then I'm going to take just one example. So maybe train images, and then train image is 0. Do you remember the first image is it was a anchor boot. So when you are trying to predict, it gives you an error. And when you have this kind of error, something was totally wrong, but actually it's not that bad, because usually this kind of error is due to the mismatch between the input data, your model's input data, and your predictions input data. So there is a very quick fix. So do you remember the slicing? So it starts from 0, but it does not include 1. So that means it's just a 0. But this is different. So when I predict, where is the predict? Anyway, yeah, it gives me 10 numbers, because my model says, yeah, the last layer of our model is the number of nodes were 10. So it gives me 10 numbers. But how can I say that, yeah, this is a anchor boot? Well, anchor boot was label, anchor boot was the last one. So from here it's 0, 1, 2, and this is the last one. And if you see the this 10 number, which one is the biggest one? If you see all these 10 numbers, I get the last one is the biggest one. So it says the biggest one is the yeah, the big output number indicate that this is going to be the answer, and it says it's 12. But it's very difficult to see the actual meaning of these 5 numbers. So when you take a break, I'm going to go over to these numbers and why, what does it mean by the logic is true here, and why we have the 10 numbers here. I'm going to explain that kind of things. So we will be back at 3:20. Okay, it's 3:20. So I'm going to start again. So the first question. So you thought the last layer for the sequential has to be 1, but here is 10. Why? Okay, that's a very good question. So let me emphasize these 4 cells. So above this cell, yeah, it's something about how can he retrieve the data set, and how can he divide it? Yeah, what's inside that? But that's just a data step. So the actual TensorFlow thing starts from here. So we are gonna make a sequential model. The input shape, because this is the image, rows and columns, and flatten is just to make a one big row. and then ReLU, and then it produce 10 numbers. So why we should have 10 numbers? Because there are 10 different classes. So in order to apply this framework to our problem, we have only 2 classes. So you have to change it 2 instead of 10. And this 10 number is, okay. So the first flatten layer, take a picture, okay, 28 by 28 as an input. And then once we go through the flattened layer, it has 7,000, I don't know the number. Uh, 784, 784, okay. 784, yeah, columns, yeah. And then we have our first layer, which has 128 nodes, and then 10 nodes at the end. So it will produce 10 numbers. And that 10 number is some is negative 12, 8, 7, and something. And in some sense, this number means the possibility that this image belongs to the category class 0. And this number is the indication that, so the bigger this number, the probability that this one belongs to this class. So it gives you some sort of a possibility, but this is not a probability. So actually what I'm going to show you is that how can we make this 10 number as a probability, so that the first number is say 92 over 1. So the probability of this image belongs to 0 is 1 over 92. And then the probability of this one is say 190. So I'm going to show you how to make this 10 number into a probability so that when you add these 10 numbers, you will get 1. So this is the meaning of why we have 10 numbers instead of 1. For the regression problems, we just wanted to make one prediction, but it needs 10 predictions in some sense. So what is the probability that this image belongs to category class 0? What is the probability that this image belongs to class 1, 2, and so forth? Actually, it doesn't matter because I'm going to classify the students in my other class, and so let me say it in this way. So we have 105 students in this class. So I'm going to take 105 students out of the total students, and then see your scores and your rankings among you. So So for the other students, yeah, it does not. For the other class students, will not affect your grade at all. Uh, okay. Uh, the TensorFlow and Keras was originally developed by two totally different groups. And actually the TensorFlow, not the group, because the TensorFlow and the Keras was originally different ones. Because yeah, TensorFlow was sponsored by Google and lots of other contributors. And Keras was developed by just one person. Oh, I cannot. So that was the original status of these two development. But Keras was so popular, was well formulated when he actually, yeah, he's the uh, male. He uh, at the first stage, he made a very nice plan to how to make all these things very nicely. So it becomes very popular. So the TensorFlow decided to hire him. So I don't know right now he is working for the TensorFlow, but some time ago he definitely worked for the TensorFlow. So from that time, the TensorFlow extend their model. So the original version of the TensorFlow does not have a keras, but at some point in time after the TensorFlow hired this guy, it has a TensorFlow keras dot something. So that's the history. And so actually you are not import keras. You are importing TensorFlow. And inside the TensorFlow, there is a keras. So maybe you can try to find the original. Still keras is developed. The keras, K-E, keras.io, yeah. So this is still the keras. But now it says, yeah, it is imported into the TensorFlow. It says from TensorFlow import keras something, but at the very first, at the beginning, the keras was not the part of the TensorFlow. Okay, and model and sequential. Sequential is a simplified version. So the 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 network structure you can make for the sequential is actually, it should be always sequential. So that means you take your output of the one layer should goes to the input of the next layer, and then the output of the next layer goes to the next layer's input. So that is the how we define the keras. So it's called the sequential model. And this is the most simplest way to define a model. But the Keras model is called a functional API, and we can define a function. So that function is, since this is a more generalized version, it always contains the sequential version. So because with the Keras model, you can make exactly the same form as we did in Keras, the sequential, but you can also make something like this that cannot be made with sequential. So the Keras model is a generalized version and sequential. But yeah, since this is the generalized version, you can do a lot more things with that, but there is some more complications because this is the generalized version. Okay. Now, I think it's time to introduce about the softmax. So I'm going to show you, I'm going to share a URL in the chat. So this is a story about me, actually. So when I first learned this function, yeah, its name was not the softmax function. It was called logistic function. And sometime later, yeah, I realized that the other people started call this one as the sigmoid function. And the sigmoid is, I don't know what sigmoid is, but the reason why they call sigmoid function is that it looks like a alphabet letter S. So that's why call this function, that's why people started call this function as a sigmoid function. But for me, it's still a logistic function. The formula for that is this one. It's 1 plus e to the negative x over I should, yeah, read from the top. So 1 over, this is the animation that I made. Yeah, it goes up and goes down. So as you can see, as x goes to, x can take from negative infinity to positive infinity, but the actual outcome is always between 0 and 1. And this is the role of the sigmoid function, and this is the role of the logistic function. So any number you are going to put inside this function, you will get a number between 0 and 1. So we can interpret it as a probability. So this is the formula. So 1 over 1 plus e to the negative x. 1 plus 1 over e to the negative x. So that's the formula for the sigmoid or logistic functions. So whatever value is here, it is always between 0 and 1. So you can interpret it as a probability. And then there is a generalized version of this function. It's called the softmax. And this name was, the terminology was named by the computer science people, the machine learning people. So it has a very, it looks like a very fancy name, but this is just a generalized version of the softmax function. I mean, the logistic function, sigmoid function, and the definition is a little bit down here, a little bit more complicated. But if you think that your J is just to 0 and 1, then you will get this one again. So maybe it's better to see the actual numbers. So it looks like this. So one is this, and the other one is this. And if you add these two fractions, you will always get 1. So that's the property of this softmax function. So now let's go back to our 10 classes example. And I said that since we have 10 classes, our output will be 10 numbers. And then when you plug in these 10 numbers into the formula that you just saw here, so it's e to the something, summation over e to the something. So let me, okay, so it's not that bad to write, but it's e the students. Let's say it's 1, 2, 3, and up to 10. Then how can you calculate this one? It's e to the 1 plus e to the 2 plus up to e to the 10 over e to the 1 is the first number, and the second one is the same lower part, but e to the 2 is the second part, and so on. So if you add all these numbers, it will be 1. And each one is between 0 and 1. So it looks like, it behaves like a probability. And this is what softmax function means. So let's go back to here. So let me define the model. Okay, yeah, another question. Just in case you have to be writing. Oh, okay. Oh. You actually, yeah, you don't have to be a member. Well, okay, I think, yeah, what I did wrong. So you have to be a member. So let me change the setting of this writing. Oh, okay, there is a friend link. Okay. The next one is a free link. But why it have to be 1? Can you just indicate each number to be a certain class of classification? Yes, you're right. Yeah. So if you don't want to be a probability, then you can just say that, okay, this number is some indication that it belongs to the category 0, the class 1, and class 2. But the better way to say that, okay, let's let me clarify in this way. So we have, let's suppose that we have only 2 classes, and it says it's 10 and it's 20. Then it's more, then this 10 and 20 means that there is this number is more likely, this data set is more likely to be in class 1. So this is the meaning of these 2 numbers. But instead of saying just these 2 numbers, maybe we can write it in this way. So this is a simplified version. So still you can get the probability. So it's 1/3, it's 2/3. So it gives you just the very similar information. So because the 20 is bigger than 10, so I believe that this data set should belongs to the class 1. But so you can say in that way, but from my perspective, I prefer to say that this data set has a probability of this amount to be in class 1. So I think, yeah, that's a yeah. Uh, I don't know. Yeah, maybe I I didn't understand what you are asking. So if my answer is not satisfactory, then you may ask your question in different ways. Oh, okay, it works. So maybe, okay, let me, maybe you may think that, okay, I'm gonna just make this 10 to be 1, and then you'll produce just one number. And then you may expect that that one number indicates 0, 1, 2, up to 9. But since if I change it to just 1, then now it becomes to a regression problem. So the output might be something like this. So for the image 1, it gives you 2.3. And for the image 2, it gives you 32.1. And for the image 3, it gives you -4. And by just looking at these numbers, it's very hard to tell it belongs to class 0 or it belongs to class 0, class 2, or class 9. It's very hard to tell. So instead of having this just one output, we wanted to have 10 outputs, and then make this 10 output to be a probability that the first number and second number, the first probability, second probability, and 10th probability, which each one indicates the probability of your data belongs to each category. Oh, okay. So let me just try a little bit different things. So I change it back to 10, so it will produce 10 numbers. And I'm going to apply a activation softmax here. Softmax. Then I can replace this loss function into the from logic to be false. So I did not tell you what it means yet, but just make two change. So the first one is the last layer. Now the activation function is softmax, and then for the loss function from logit is false. And then let me rerun this one. So it's a model, and we compile it, and then we fit the model. Okay, now we have 91% accuracy, which is very similar to the previous one, because if I change it to activation is softmax and from logit is false, it is basically the same thing as before. So what's the difference between these two? Okay, let me predict with my trained model. So before I use my modified model, it produced the output of this format, so -10 and 12. But now I can see the output is actually probability. It doesn't look like a probability, but you see the e to the negative something, e to the negative something is is a very small number. So the biggest number here is actually this one. And if we read it in our ordinary way, it's 0.99917 something. So the first image is the have a 99% probability of being the last category. So let me change it to another one. So let's say it's 1, 2, 2. That means I'm going to take the first image, the second image, the index 1, and predict. Okay, now the numbers have been changed, and what is the biggest one? And I think this one. So the second image, the probability of the second image, the probability of a second image being class 0 is 99%. So let me see. Yeah, this is true. So instead of doing this one, I'm going to see the first one. Yeah, it looks like a t-shirt. So maybe I'm going to take some random 100th, I don't know, not one, the index 100 image is, I think it's a bag. So let's go to down. So 0 was, it's okay, so 100 and 101. Oh, it's almost perfect probability of it's 9, it's 8. So let's go to the class name. Yeah, it's a bag. So it gives you the probability of each category or each class. So how can we do that? So actually you can use the softmax activation at your final layer. Then all the number is changed, all the numbers are changed to probability. Then you don't have to set this from logit to be true because it is already a probability. But without this, it's not a probability. The output is not a probability. Then you need to tell your loss function, okay, it's not a probability. And the original number is in this original number in this the original format is called a logit. So from logit, yes, true. So that means the number here is not a probability. But if you put if you make your output to be a probability, then from logit, oh well, it's not. It's already a probability, so you don't have to worry about it. So that's the meaning of this one. So Now you can use this idea to the third competition. And actually, that's it. So maybe, yeah, I can change it to two classes. So because our problem is classification between two classes. So let me change it to, and then I want to make it as activation is softmax. So for me, it's more intuitive to make it probability, and then it's not from probability. So I said it's not from logic, so it's false. And if you try to run this one, at first it looks fine, but if you really try to this one, you will get an error. So why you get an error? Because your train labels, your input is okay. So whether, your input is okay. So whether you change it to 2 or a 3, but your train labels has 10 different values. So remember that train labels is, it's 90035. So it's 10 different numbers. So maybe I can change it to 2 different numbers just for explanation. So train labels, and do you remember what the percent sign means? It was modulus. So it's a divide. It produced the remainder of your division. So if you divide a number with 2, the remainder will be either 0 or 1. So I just transform the data set. And then since I transform the data set, I can, if I rerun this model.fit, I got the working code. And it's really nice. It's it's over 98% accuracy. And that's because it's much easier to classify 2 different things rather than 10 different classes. So it's much better. Okay. Okay. So logic, true, false, what does it mean? Logic is the original number, and you can transform logic to probability with softmax function. So in our program, when we define our model, if I specify that, okay, I'm going to apply the softmax at the end, then means the output will be a probability. Then I don't have to say that my loss function is from logic. And you may think that, this is okay. Is it from logic? No, it's not from logic because I already changed it to probability. So from logic is false. But if I did not use the softmax function at the end, then it produces the the original numbers. Then I need to say my loss function is it from logit? Actually, yes. So I have to say true. So that the loss function can take care of this number to transform into a probability and something like that. And then the TensorFlow says that there is a little bit difference between performance, but for me, that difference is not so important. So my preferred way is to use this one. So I apply the softmax function directly to the node and say that from logit is no, I already transform it to the probability. So from logit is false. Okay, let's go back to the competition. So I'm going to make a new notebook. Oh, there is a one. This is the one that I did the last time. Okay. Is it? Did I? Yeah, I think so. Okay, copy and edit. Okay, so first we read the files. Read the files and import the necessary libraries, and then read the data set and see what's inside and make a copy, and then take out column 5 and take out column 3. And since we don't need the ID column, we just take it out and then see our data manipulation is correct. So it's df, it's the original version. And then, so my X has 5 columns, and the column 3 is here, and column 5 is here. And I said, this is my first model, but I'm gonna show you, how to make my first model to predict column 8. Oh, do I have a column 8? Oh, I don't have a column 8 yet here. So okay, let me go back to the column. Okay, let me go to the competition 3. Let's go to the competition 3. And I'm gonna make a new notebook. to see what's inside. And then I'm going to import TensorFlow STF. I'm going to import, just one. And df is read CSV and train.csv. Oh, it's wow. And then see what's inside. And there is a column 8, which is our target. Actually, for this problem, there are 2 targets, but I'm gonna say, the column 8 is my target right now. So make the features FEAT features is df copy okay, and then column 8 is my target. So I need to practice typing features dot pop column 8. And I don't need IDs, so features pop ID. Okay, of course I have to eliminate the column 3, and so forth, but I'm just gonna skip, and I just pretend that I have the features and my column 8 to show you how to do the classification. In order to do the classification, okay, this time I'm gonna make a model instead of a sequential. So I need to define my input, and my input is TF keras input, and the shape is, in this case, shape is 1, 2, 3, 4, 5, 6, 7. So 7. And then TF keras Y, TF keras dense, and activation is relu, and it takes my input. So instead of writing just the input, I said my input. And then I'm going to make keras dense layer, which has 2 nodes, and activation is softmax. And Y is okay, then this Y is actually my output. So it's my output. And then TF, okay, so I'm gonna make my model is TF keras model, and input is my input, and output is my output. And I don't have to specify the names. And I want to see how it looks like. Smart dot summary. Okay, there is an error. TF Keras does not have attribute dense. That's right, because I forgot to add the layers. Layers. And here, layers. Yeah, this is my model. So I have an input layer and a dense layer, and its output is a 2-node. So I define my model, and then I need to compile. So my model dot compile, and the loss is I don't remember. I need to go back to the QRM. My loss is this one. Actually, I just wanted to copy all of them, because the compilation, the compile is actually the same. So instead of the model, I need to say that this is my model, because I named it as my underscore model compile. Optimizer is Adam, loss is TF Keras losses, sparse categorical, and from logit, no, because I already applied the softmax activation, so it is already changed to the probability. So from logit is false, and I'm gonna add some accuracy as my metric. So it's okay, and then I need to fit. So model fit, and what is my x? My x name was features, and my y was column 8, and I wanted to see it works or not. So epochs is only 2. Yeah, it works. And accuracy is 96%. So it's great, because actually since I use all the columns, it looks like it is working very well. But since my test data set, there are some columns are missing, the performance will not as great as this one. So basically, this is the classification. So any questions? Okay. Yes, I will. Yeah, I will upload the video as soon as possible, because I will not be available from next, I don't know, it's Tuesday, Wednesday. So, and I cannot answer, I cannot respond to your emails also. So if you have something to ask, yeah, please send me a little bit earlier, or and if I don't reply your emails, don't hate me. I will not be able to see your emails. Yes, that's exactly what I want. What I want, yeah. So the test data set does not have column 3 and 5. So you first predict these two columns, and then use these columns for predict. It's not predict it to classify column 8. So yeah, your understanding is correct. Sure. Let me see. Uh, the reason I did not share with you is that you need to type. So instead of sharing, I wanted to show you this one. So actually, the modeling part is this one, and then the compile is I just copy the compile section from the core app, and then model fit is obvious. So this is the modeling part, and before that is just data manipulation. When I was a high school student, or when I was young, so my teacher always said me, you have if you wanted to remember or if you wanted to learn something, you have to write it. So and so for example, when I try to memorize the English words, I try to write something. And nowadays we don't write much, we type. So that's why I don't want to share. I'm not going to share the code, because now so that's called the muscle memory. So when you try to type and your muscle learns something, so by just looking at the code and just editing some of them is not sufficient to learn something. So instead of you watch it and then try to type everything. The matrix is just some monitoring tool. So whether you're how to see how your model training works. So for example, we can choose our matrix as the accuracy. Where is that? Yeah, that accuracy here. But we can also choose another matrix. But I don't know yet what kind of matrix are available in TensorFlow. So maybe we can say TF matrix, matrix. Then it offers you lots of different matrix. So for example, AUC, accuracy, binary accuracy, or cosine similarity. I don't know what all of this means, but it gives you some sort of a matrix. So for example, the precisions. So there are so many of them. So the one thing that is very obvious from the word is accuracy. So that's the meaning of the matrix. Okay, thank you. Okay. Okay. So note. Yes. So take a picture and then try to type. Okay, I think that's not enough, but uh, I hope you are trying to learn by searching. Yeah, search the internet, and you may think that for example, the scikit-learn is much more easier, but actually, what you can do with scikit-learn, you can always do it with the TensorFlow. So that's why I wanted to teach you about the TensorFlow. For example, some students say that the sklearn, yeah, this is called the scikit-learn, and some students say, oh, this is much easier. For example, the random forest. But if you search the TensorFlow and random forest, I don't know why it is written in, why I see this one as Korean. So maybe I can change it to English. And there is a way to do the same thing in the TensorFlow. So for example, the random forest, yeah, you don't have to know what random forest is, but if you have a random forest, then that is gonna be just a one layer. And then since you know how to build the model, not just the sequential, you apply the random forest and then take the output of the random forest to another layer and send it to another way. So that's the way you build up your models. So this scikit-learn is yeah, it's pretty nice because it is older than the TensorFlow. So in older times, lots of people wanted to use the scikit-learn, but nowadays it's a little bit outdated, and it's so in some sense it deals with the very elementary uh, machine learning techniques. So if you know some part of the scikit-learn, probably that you may think that that's just one layer in TensorFlow network.